Hello, this is Jack Jackson. In this video, we're going to be investigating the question, does differentiability imply continuity? In other words, if it is differentiable, does it have to be continuous at a point? So we're going to investigate this with three different functions here. And they all have some type of discontinuity. We have a jump discontinuity in this one, a whole or removable discontinuity in that one, and here we have a vertical asymptote with an isolated point down here. In all three cases, the function is defined everywhere. Specifically, it's defined at a f of a, which is the point 1, -3 in all three examples. Okay? So we have this point 1, -3. Now, certainly the function is defined there. For the derivative to be defined, the function has to be defined there, because to do the derivative, remember, it's the limit of a difference quotient. The limit is h approaches 0, f of x, or a plus h minus f of a over h. And notice it has f of a in the difference quotient itself. And so if f of a doesn't exist, then there's no hope. So we know the function has to exist there if the derivative is going to exist. If the function is undefined, the derivative is undefined. Well, the next step up from that would be, well, what if the function does the function have to be continuous there? And let's look at what happens here. So we're going to be taking this point here, b, which can be anywhere on the function. Okay, and let's look at what happens to the slopes of these secant lines. So the slopes of these secant lines where it goes through the point of interest are actually difference quotients. And if you look here, we're coming in from this side. It does appear to be approaching actually some number, something here. It looks like it has a slope of, well, -4 is what it looks like it's approaching there. But look what happens from the other side. We have this jump discontinuity. As we're coming in here, the slopes just keep getting bigger and bigger and bigger. There were negative slopes over here, positive slopes over here, but the slopes are approaching infinity. As we approach from this side, that line is approaching a vertical line which doesn't have a slope. The slope is undefined. So at least from one side here, we notice that the limit that defines the derivative is undefined. So the full limit that defines the derivative, the limit of the difference quotients, is undefined. And so, in fact, the derivative does not exist. What about if you have a hole in the graph? Well, if we have a hole in the graph, if the function is undefined there, then we know the derivative doesn't exist. But let's suppose the function is defined with the same x value, but a different y value there. What happens is we look at this. Well, the problem is here we have some negative slopes. As we're approaching from the left, we're approaching a vertical line, but with a slope of, well, approaching negative infinity. Whereas over here we have positive slopes, and we're coming in, we're approaching a vertical line. So in some sense, that these lines are approaching a single, sort of like a tangent line, I guess. But that tangent line, if you want to call it that, the limit of those secant lines does not have a slope. It's a vertical line. So once again, one or both of the one-sided limits of the difference quotient are either infinity or minus infinity, and no derivative exists there. Here's another example where we have vertical asymptotes. Again, if the function's undefined at x equals 1, then certainly there's no derivative there. But let's suppose we have some isolated point here. And we look here again. The derivative is the limit of the slopes of these secant lines is approaching infinity from this side, but it's approaching negative infinity from this side. Again, it's approaching a line. Either way, we're approaching a vertical tangent line, if you want to call it that, the limit of these secant lines, but it is not a line that has a slope. So the derivative is undefined there. So whether you have a vertical asymptote, a hole in the graph, removable discontinuity, or a jump discontinuity, no matter what, we're always going to, at least from one side, we're going to get a one-sided limit of the difference quotient to approach infinity or minus infinity anytime we have any kind of discontinuity, and so the derivative is not going to exist. So it turns out that if the derivative is going to exist, the function has to exist there, and the graph has to be continuous at that point. So differentiability, the set of differentiable functions is a subset of the set of continuous functions. So then that brings us, what about the other direction, the converse? If it's differentiable at the point, it has to be continuous. What about the other way around? If it's continuous, does it have to be differentiable? We'll investigate that in another video and with another GeoGebra sketch like this one.